I've talked about how using the diffraction grating, where you have many slits very closely spaced, as close as maybe 1 micrometer apart, you could get fringes, interference fringes, that are very narrow lines, so that you can measure the positions, the distance between two fringes very accurately, and then using the formula, you would then be able to calculate the wavelength of the light that produce these fringes. So let me now take a look at an example of how we would actually use this to work out a wavelength. Let me start with a grating. So this will be a piece of glass with many lines, very closely spaced line drawn along it, and we would have a screen, perhaps some distance away. The screen. Suppose now that I have a yellow, a red light, right? A red beam of light coming through here. So this is, we can imagine that this is a narrow beam of light, but because the spacing between slits are so close, a narrow beam, maybe 1 millimeter wide perhaps, would already cover many slits. So I'm going to assume that this is a grating with, say, 1,000 lines. 1,000 lines per millimeter. Okay, so this red beam of light would spread out, interfere, the light from each slit will interfere with one another and produce the fringes at the screen. So at the screen, we would expect at the center a red fringe, and then this, and then further up we would expect another red fringe, then on the other side red fringe, and then maybe some distance further away there'll be another one. So this is where n, center one is when n is 0. First one on the either side is when n is 1. The path difference is 1 wavelength. Okay. Suppose now that right, I want to measure the wavelength. I want to measure the wavelength of this red light. So to measure this, I can use the formula. I can use the formula d sine theta is equal to n lambda. So if I'm going to take n to be 1, the first order fringe, I would have to find d and theta. D we can find from this information. Just take 1 mm, divide by 1,000. Theta we would have to actually measure this. So imagine that we have set up this experiment with the grating on one side, the screen on the other side. We'll have to actually measure the angle between, let's say, this straight line that goes directly from the grating to the center fringe, and another straight line that goes to the first fringe. So these are the two main beams of light that spread out and go to the screen. So this is the angle that we need to measure. I call this theta. That's the angle. So we can set this up, observe the fringes, and maybe use a protractor to measure this angle. And for red light, we would find that this angle, red light and this grating with this number of lines per mm, we would find that this angle is, let's see, it's about 44. We would find that this angle is about 44.4 degrees. Let me write it out here next to this. 44.4 degrees. Okay, so now that suppose that we have measured this angle, it's 44.4 degrees. We want to find, okay, let me just write this out. That's 44.4 degrees. That's what we want to find. And I'm doing it for the first fringe, so n is just 1. And I also need d. Now to find d, that's just the spacing between the lines or between the slits. So d would be 1 mm divided by 1000. Okay, so that would be 1 micrometer. So now I have all I need to find lambda. Therefore, lambda is equal to, right, n is just 1, so lambda times 1 is lambda. So therefore, lambda is just equal to 1 micrometer times this. Okay, so I'll have 1 micrometer times sine of 44.4 degrees. Now, if you use a calculator to calculate this, you'll find that the answer is very close to 700 nanometers. So that's the wavelength of red light. Let me write this down. So the wavelength of red light, let me just use red color, is 700 nanometer. Now let me look at another example where instead of red light, I have green light. No. Now let me say violet light. So I have violet light. Instead of green light, I have violet light, and if I have violet light has a different wavelength. Violet light has a different wavelength, and because of that, actually violet light has a shorter wavelength. So because the wavelength is shorter, this angle would also be smaller according to this formula. So therefore, while we would still have a beam, a fringe at the center for the violet light, there would be a smaller angle for the first order fringe. You would expect a smaller angle. Now if you repeat this experiment for a violet light, for example, so let's say I find that this time if I measure the angle, let's say I find 23.6 degrees. Okay, let's say that's what I find. There'll be a violet light at the center instead of the red light. Okay, so that's what I find. And if I now want to calculate the wavelength of this violet light, I could use the same formula. N is again 1, but I have a different angle this time. The angle this time is 23.6 degrees instead. Now D, the spacing between the slits, is still the same. I'm using the same grating. So that's the only change. The angle is changed to a smaller value. Now if I repeat this calculation, so instead of 44.4, I'll use 23.6 degrees. Then if you repeat this calculation, you'll find that the answer is very close to 400 nanometer. So violet light has a shorter wavelength. Okay, now what I'm going to do now is this. I'm going to change this whole thing to white light. I'm going to change it to white light. So let's see. Let me clear up some of the and clear up some of these lines. Okay, and suppose that I have white light coming in, or sunlight. Suppose that I have a ray of sunlight coming through a small hole in my window, just like what Newton used when he experimented with his prism and discovered that sunlight would split into the colors of the rainbow. So let's say I have a narrow beam of sunlight coming in through a small hole in my window and falling on this grating. So what do I expect to see? Well, we know that sunlight is made up of all the different colors between violet and red. Okay, but whatever the color, whatever the wavelength, we know that the light would always have a central fringe at n equal to 0. So all of that light will produce a fringe at the center. So they would all overlap at the center and produce a fringe, and that must be white in color because all the color comes here. Okay. Now what about the first fringe? What about here? Well, if you're talking about sunlight, we have the colors of the rainbow, all the way from red to violet. Okay, red to violet. So we already know the positions of, if we just have red light, we already know the position of the fringe, and we know its position of this first fringe if we have just violet light. So we can imagine that if we have other colors in between, then surely the fringe of that color has to be somewhere in between. So let's think of an example. Let's say, let's think about the yellow parts. The yellow parts of the color, of this color coming in from the sunlight. So it would be somewhere in between, maybe a little bit closer to the red light perhaps, and it would produce a fringe maybe somewhere there. Okay. How about the green light? Okay, let's have a look at the green light. So the green light will be maybe a little bit further down, okay, somewhere between the yellow and the violet. That would produce another fringe a bit further down. Oh, and then we have a blue light. We could have a blue light as well. So that blue light would again go out at a slightly different angle, and it would be somewhere below the green light, between the green and the violet. So that's what we would have. We would have the colors of the rainbow all spread out over here. Alright, in the part where they're supposed to form the first order fringe, where n is equal to 1. Okay, so what do we have now? We have the grating acting as if it's like a prism, right? So that's an interesting one. So this is like a prism. It's behaving like a prism. It splits up the light into the colors of the rainbow. And in fact, I would say that it is even better than a prism, because if you look at these two angles, right, these two angles are tells us the angles for the red light and for the violet light, for the two ends of the spectrum. Now the difference between these two, if you subtract them, you find that the difference is okay. I'm just going to put down a rough value. It's about 20 degrees, right? So that's the angle, angular spread, the spread in angle between the two ends of the spectrum. Now, if you think of a prism, right? If you talk about a prism, a prism is a piece of triangular piece of glass, okay, and if white light comes through a prism, okay, as we know, it splits up into the colors of the rainbow. So we get blue, we get red, and then we get all the other colors until we go to violet. Right, so we get all the other colors in between. Now, this angle, this spread angle, if we use a glass prism, or a prism that is made of glass, if you actually try this out and measure this angle, you'll find that this angle here between the red and the violet light, the two ends of the spectrum, is only about 3 degrees, maybe 2 to 3 degrees. It's almost 10 times smaller than if you use the grating. So in that sense, the grating is much better than the prism. If you want to produce a spectrum of light, it will really spread out the spectrum so that you can see all the colors very clearly. And this ability of the grating to do this is very useful, because if you can spread light out in the prism, you can see what colors there are, and there are many uses. For example, you can use it to tell the temperature of a hot object, right? A very hot and glowing object would have a different color depending on that it glows with, depending on its temperature. Or we can use it to tell even the elements, the chemical elements in a substance, right? From the light coming out from the chemical, because the chemical will produce a different colors in the spectrum. We'll learn about this in a later session. So if you're talking about producing spectrum of light, therefore the diffraction grating clearly works a lot better than a prism. But that's not to say that the prism is not of any use anymore. Prism can be used in many other applications, in making, say, as part of optical lenses, cameras, and so on and so on.